So hey guys, I'm Jaydeep here. This will be a very basic video regarding the mean standard deviation and variance. Those of who know this concept can skip this video, it's fine. Those who want to refresh just the concept, so let's go through it. So what is the mean? Mean is the sum of all values divided by the number of values, right? So if I have total n number of data points, I will just add all the values and divide it by n, right? So what it gives is mix something called as average. What value I can expect if I pick one of the number randomly, what value I can expect. So it's given by mu, the value which you can expect if you choose any number randomly from the given values, right? Now it doesn't mean that average has to be in your data point, okay? That's very important thing. Mean, you might get some number as a mean, but that really doesn't mean that that number has to be in your data points, right? It may or may not be, right? Now what are the pros of mean? It's very simple to calculate because you just need to add the numbers and divide them by n, right? And it is not much affected by the sampling fluctuations, right? I will explain sampling and population, for those of who don't know, but yeah, it doesn't get affected by the sampling fluctuations, right? Now what are the cons? Cons is that it's highly sensitive to the extreme values. Suppose I am having numbers 1, 2, 3, 4, 5, right? And what will be the average? It will be 15 by 5, it will be 3. But rather if I had 1, 2, 3, 4, 50, it would be 60 by 5, right? And it would be 12. See, such a drastic difference just by the corruption of one value, right? From 5 we got 50 as a corrupted value, so our mean shifted by a very huge amount, right? Now the 12 is not a correct representation of the values we have over here. Now this was a very small example just of 5 values. Imagine that you are having, suppose say, 1000 values, right? And all are in the range from 1 to 10 except one value which is equivalent to say 98,000, right? Now this will kill the mean so badly that we wouldn't be able to guess what was the actual numbers in the data set, right? So this is very tough problem which we have to face when we are using the mean, right? Now also the data point which I just explained here, see here, the average came out to be 12, but is the 12 in our data set? No, 12 is not there in our data points. But however, in this case, in the first case, the value come out to be 3 and it is in our data set, right? So this is the pro and con of the mean, right? So keep that thing in mind. Now what is a variance, right? See, suppose I have two sets, 0, -1, 0, 1, and the other is -100, 0, 100. Both will be having average as in 0, right? Because addition itself will be 0. But from the average or the value 0, you can't really tell me how values are away from each other, or rather how values are away from the mean, right? Because we are taking mean into account. Now in order to understand how much values are away from the mean, we need something called as variance, okay? So variance helps us to understand how far away the values are from the mean. So if you take the variance over here, it will be just 2 by 3, but however here story would be different. It would be 10 to the power 4 multiplied by 2 upon 3. Now you can see that this is much larger than compared to 2 by 3, right? So here we understood that the variance of a second data set is higher, meaning that the values are very away from the mean, and here the variance was low. So we understood that okay, values are somewhat very closer to the mean value. So that's the essence. Variance gives us understanding how far away the values are from the mean, okay? Now the good thing is that it treats all deviation from mean as the same. So -1, the deviation between -1 and 0 is 1, as an quantity, and deviation between 1 and 0 is also 1. So irrespective of direction, right, we got the same value. So that's a good thing. Otherwise, if we would have treated the direction as an parameter, then we might end up with zero variance, right? Now there are some cons. See, it's also get highly influenced by the value which are very far away from the mean, and less by those which are closer to mean, right? Because the value which are closer to mean will be contributing less to the overall sum, and value which are far from mean will be calculating very high to the calculation of a variance, right? So that's very con of a variance, because one extreme value is enough to kill all the uh, idea or the intuition you were trying to build regarding the data set. Now comes the second thing. Scale is different from that of the input data. What I mean here is that suppose you had in original data the height in centimeter of the students, right? Now when you are measuring variance, you can see that here we are taking the square, right? So what will be variance? Variance will be in terms of centimeter square, right? So it is different from the original units. Originally we were measuring the height in terms of centimeters in the unit centimeter, but now variance is in terms of centimeter square, so units are different, right? So that's one con, because in exploratory data analysis it might be our very requirement that the unit should be same so that we can compare things side by side, right? And also the low interpretability. Now this is because we are directly using the squares, and whenever we are using the square, we understand that extreme values will kill the variance in a very uh, dramatic way. So in that case we won't be able to understand the whether the data is itself having a high variance, or it is just a single value which is causing the high variance problem, right? Now there is a something called a standard deviation. It's a root over the variance, what we just saw variance above. So what are the pros? Its unit is same as that of the input. See, because what variance give is centimeter square, what we are applying is root, so what we are getting is centimeter, right? And so it definitely improves the interpretability, because we are here we are taking the square root. So that's very good thing regarding the standard deviation. And it's again the same con it also had, is that it also suffers from the extreme values, because extreme values will definitely make the square terms larger, right? And as the square terms goes larger, variance increases, and as the variance increases, our standard deviation also increases. So it also suffers the same problem, right? Now here is the code, guys. So what I have done is that from the iris data set, I have took the uh, data which has the label setosa, right? And how do we do that? Iris species where our setosa, just take those values, right? So iris species equals to if setosa, then we take those values into the setosa. So setosa is a new data frame where all the instances of iris dataset having labeled as setosa are stored. Similarly for virginica and for the versicolor. And now we just plot their mean, variance, and the standard deviation of the sepal length of setosa. So you can see those three values, right? So I hope you guys have enjoyed this video. It would be very nice if you subscribe, turn off that notification thing. Take care of your time and take care of yourself.